Hello, we are the group Cyanobacteria. Today we will introduce our project, fractals. What is a fractal? In fact, there is some disagreement among mathematicians about how the concept of a fractal should be formally defined. But there are some common features of fractals. A limited description of fractal by Benoit B. Mandelbrot is a rough or fragmented geometric shape that can be split into parts, each of which is at least approximately a reduced size copy of the whole. Here are some characteristics of fractals. First, self-similarity, including exact, quasi, statistical similarity. We can see it clearly in the video on the left. Second, detailed structure in small scales. We can see it in the video on the right. Third, a fractal may have non-integer dimension, which we will discuss later. Fourth, the shape of fractal is often irregular. Last, a fractal often have simple and recursive definitions. We can see that there are different types of fractals. We can categorize them into some classes by ways of generating them. There are 5 such classes which are self-similar: escape time, strange attractors, random and natural fractals. The most common type of fractals is self-similar fractals, whose part is often exactly similar to the whole. Here are 4 ways to generate them. The first one is by node replacement and edge replacement. This is the most intuitive way to draw fractals. Repeatedly replace nodes or edges in the curve. The curve for each replacement is called a generator. We can see that in the following pictures and video. The second one is called iterated function systems. Start with an initial image or piece of geometry. By copying, scaling, rotating and other transformations, generate a fractal. This method can be described by matrix. The third way is called branching fractal trees and the fourth way is called L systems. Next we will talk about the escape time fractals. These fractals are generated by iterating a formula or recurrence relation at each point in a space. For example, the Mandelbrot set is the set of complex number C for which the following function does not diverge when iterated from z equals to 0. Since the number is in complex plane, we can draw them on a geometric plane, by using different color for points or complex numbers that diverge and converge. We've implemented a dynamic Mandelbrot set browser. Users can zoom into any part. The principle of this program is easy. Simply iterate the function for some times, and check whether it diverges. Here we will show you how to use the browser. We can zoom in, out, we can also stop, and when we stop the zooming, we will get higher resolution. We can click Help to get more information. Next we will talk about strange attractors. When we repeatedly iterate a formula, it sometimes evolves into one or some certain values despite the starting value, that is, convergent. These values are called attractors. Some attractors have fractal structures, which are called strange attractors. Unlike other fractals, these type of fractals can be smooth. Here's an example of strange attractor, the Ikeda map. It can be described as smoothly pilling up surfaces. Here's a video to show the process of iterating and how the shape is generated. Next we will talk about random and natural fractals. Generally speaking, a random fractal is just a fractal generated by stochastic rules. For example, the Brownian tree. The trace of Brownian motion also belongs to this class. A natural fractal is a fractal that generated naturally. For example, the river basin, we can see that each tributary of has the similar structure with the main stream. A fractal can have limited area with infinite perimeter. A fractal curve may fill up the whole plane. The principle behind these is that they have non-integer dimensions. A fractal dimension is a ratio providing a statistical index of complexity comparing how detail in a pattern changes with the scale at which it is measured. Here's a list of dimension of different types of fractals. Generally speaking, for a fractal curve whose topological dimension equals to 1, if its fractal dimension is higher, it looks denser in a plane. If its fractal dimension is 2, it fills up parts of the plane. So how to calculate the fractal dimensions? Here's a way to calculate dimensions of self-similar fractal curves generated by edge replacement. Suppose n is the summed square of all the segment lengths of the generator, see the picture, and L is the distance between the entrance and exit of the generator. The fractal dimension of the fractal curve is log L divided by log n. We can verify that for non-fractal shapes, this method is in line with intuition if we extend it into planes and cubes, that is, 1 for lines, 2 for planes, 3 for cubes. For other types of fractals, a way to estimate fractal dimension is by box counting. Use small boxes to cover the shape and calculate the dimension by the following formula, where epsilon the side length of the boxes. We can verify that for non-fractal shapes, this method is also in line with intuition, that is, 1 for lines, 2 for planes, 3 for cubes. We've implemented an automatically estimating fractal dimension program. The principle is to count the number of pixels which belongs to the fractal in a bitmap. We estimated the dimension of Ikeda map as 1.79 and Mandelbrot's at 1.98, consistent with the data from Wikipedia in general. Thank you. Vocal by Microsoft TDS.